Okay, now we're going to look at some problems. And these problems are going to kind of start with the basics and then they're going to go into the final equation. None of this is too extreme as far as the math is concerned, so hopefully you just understand what we're doing in each situation. Before we tackle any of the problems, though, we need to talk about one unit of measurement, which is electron volts. Right? Electron volts is another way to measure energy. Now, I'm hoping we understand what an electron volt is as I go through the definition. But if all we know is that it's another way to measure energy, it's another unit for energy, well, then we're still going to do all right. An electron volt equals 1.602 times 10 to the negative 19 joules, right? And an electron volt is important because for all of these problems, or anytime we're dealing with things on this atomic scale, protons, neutrons, electrons, there's just not a lot of energy there, right? So, the kinetic energy that an electron has is going to be tiny. And the energy required to break an electron free is also going to be tiny, right? These are very small amounts of energy. So, lots of times if we measure them in joules, they're going to be tiny, tiny numbers, right? So we tend to use electron volts just so it's in the right scale, right? We'll see something like if it's something that has 2 electron volts, well, then that's a tiny amount of joules, but 2 electron volts is easy to work with, right? So what is an electron volt? Specifically, an electron volt is the amount of energy an electron gains when accelerated by 1 volt. So that's what it is. And we're going to apply that definition later on. And it's hopefully going to save some time. But let's go through. We're going to read the questions real quick so you see what we're going to work on. And then I'll go through, I'll read them again, and then I'll show you the answer, right? So question number 1, what is the energy of a photon that comes from light with a wavelength of 500 nanometers? Question number 1. Question number 2, the photoelectric effect produces a current of 1.2 amps. How many electrons are breaking free per second? Problem 3, the stop-in voltage of 0.5 volts is produced when a certain light is shined on a certain surface. What is the kinetic energy of the electrons when they break free? And the last question we are going to look at is what is the work function of a material that has a stop-in voltage of 0.3 volts when light of 430 nanometers is shined onto it? All right, so let's look at number 1. Number 1 is what is the energy of a photon that comes from light with a wavelength of 500 nanometers? So we are looking for the energy of the photons. Again, we don't know how many photons are produced. What we do know is how much energy every photon has. So I'm going to wait 1 second. If you want to pause this and try the problem on your own, you certainly can, and then I will put up the answer. All right, so the equation is the first equation we had from the last lecture. The energy of the photon equals Planck's constant times frequency, or we could say the energy of the photon equals the speed of Planck's constant times the speed of light divided by the wavelength. Again, we can go between frequency and wavelength by using the wave speed equation. And again, like I said a bunch of times last time, right? Even though we're talking about photons and we're saying that light is photons and not waves, we're still using all these wave measurements to get the energy of photons. So I can plug these in. I know the constant, 6.626 times 10 to the negative 34 joule seconds. I know the speed of light, 3 times 10 to the 8th meters per second. And then 500 nanometers is the same as 500 times 10 to the negative 9 meters. When I look at unit analysis, all I'm left with is joules, which is good because I'm looking for the energy of a photon. So 3.976 times 10 to the negative 19 joules. So there's my answer, but lots of times, again, we wanted an electron volt, so I'm going to do the conversion to electron volts because this is a very tiny number and it's kind of a hard number to deal with on a calculator and stuff, but if I convert it to electron volts, divided by 1.602 times 10 to the negative 19 joules, then this photon has an energy of 2.48 electron volts. There is my first problem. Problem number 2, the photoelectric effect produces a current of 1.2 amps. How many electrons are breaking free per second? So we know when we shine light onto a surface, if the conditions are set up correctly, then electrons will break free, right? So if I make all the electrons go in one direction, then we can measure the flow, how many electrons are breaking free per second. And this is telling us it is 1.2 amps. Or if you want to work through this, again, I'll give you a couple seconds before I change to the answer. All All right, so it's 1.2 amps, which is the same as 1.2 coulombs per second. And then if I set that up, 1.2 coulombs per second, and this number pops up all the time, 1.602 times negative 19 coulombs per electron. So coulombs will cancel out. I'll be left with electrons per second. 7.49 times 10 to the 18 electrons are breaking free every second due to the photoelectric effect, right? So this is really more of a unit analysis question than it is anything else. All right, question 3, make some assumptions, right? A stopping voltage of 0.5 is produced when a certain light is shined on a certain surface. So we know we have in the photoelectric effect, we know we have the photoelectric effect because electrons are breaking free, and it takes a 0.5 volt stopping voltage to stop the electrons from hitting the other plate. And it's a voltage, so it's the change in potential energy per charge. So what we're doing is we're changing the kinetic energy to potential energy, right? They're moving in one direction, we make them stop, and then they start coming back, right? So we're changing the kinetic energy to potential energy. Um, so I'll give you a second before I put the answer on. All right, so for this one, if we understood the definition of an electron volt, then we could save a lot of time. So Adona, pay attention here, because I'm trying to save you some time so you don't have to go through all this math every time. When I look at the answer, well, 0.5 volts is the same as 0.5 joules per coulomb. And I know how many coulombs are in an electron, so if I set this up, it's going to be joules per electron. Every electron must have 8.01 times 10 to the negative 20 joules of kinetic energy. That's what it's telling us, how much kinetic energy we have. And if I want to leave it that way, it's perfectly fine, but I could actually save myself math, right? If I leave this in electron volts, this works out well, because if I know how much energy there is per electron, and I know how many joules there are per electron volt, well, I multiply by 1.602 times 10 to the negative 19 coulombs, and then here I'm dividing by 1.602 times 10 to the negative 19 joules to get to electron volts. And look at this, a stopping voltage of 0.5 volts produces a kinetic energy of 0.5 electron volts, right? They're not the same things, but if I look at the math, it works out to be the same number. So really, if I understand what a stopping voltage is, I don't really have to do any math here. 0.5 volts is 0.5 electron volts of kinetic energy. Makes it nice and easy. Okay, question 4. What is the work function of a material that has a stopping voltage of 0.3 volts when light of 430 nanometers is shined onto it? Again, if you want to try it first before I put through the answer, now would be a good time to pause it. Okay, so this problem puts together everything that we talked about in the first lecture, right? We have to understand how to get the energy of the photon, which we did in problem 1. We have to understand what the stopping voltage gets us, which was in problem 3. And then we've got to put that all together into the one equation that relates them all. So the equation is the energy of the photon equals the kinetic energy of the electron plus the work function of the electron. The energy of the photon, right, when the photon gives the electron energy, two things happen. It breaks free, that takes a certain amount of energy, which is the work function. After it breaks free, any energy left over must equal the kinetic energy that that electron has, right? So looking at it, this is the general equation, but if I look at it a little more specifically, I can get the energy of the photon because what do I know? I know the wavelength, I know the speed of light, I know Planck's constant, I can get all of that, right? When I do this, this is what I have in blue. Again, I'm going to convert it to electron volts because they're just easier to work with. And also when I do the next part, that's much easier if I leave it in electron volts. So it works out that the energy of the photon must be 2.89 electron volts, right? Again, all the units cancel out except for electron volts. So every photon that comes from light, that's 430 nanometers, photons have an energy of 2.89 electron volts. Well, if we look at the problem again, the stopping voltage was 0.3 volts. So what's the kinetic energy of the electrons? Well, it must be 0.3 electron volts. And that goes back to the last problem. I can show that math again, but if I figure it out, right, I get the same thing um, in electron volts. So I know the total energy is 2.89. This is how much kinetic energy the electrons have after they break free. So if I just take the 2.89 and subtract 0.3, whatever's left over must have been the energy that broke the electron free, or it must have been the work function of that. Okay, so there are the problems. You can certainly do the law and kappa problems that are on photoelectric effect. The next section will look at a similar topic, but not exactly the same one.